So I'd like to welcome Thomas Vondra here to talk about improving fast path locking in PostgreSQL 8. Thomas Vondra has been a long time community member and contributor, so welcome to PGConf. You're ready to start when you are.
Yeah, thanks for the introduction. One warning, I have some, charts and everything in the slides, so I would advise actually sitting closer to the podium, but up to you, of course, right? Another warning is that I submitted a talk for 25 minutes, then I completely forgot about that, and I prepared the talk for 45 minutes, which was a challenge because it's not such a topic for like 45 minutes, but I will fix that by just talking very fast, so that's fine. Obviously, I do have an accent, so if you don't understand something because of that, let me know. I will repeat that with exactly the same accent, right? So let's start. What is the agenda of this talk? What I'm going to talk about is a particular improvement, a fairly small improvement in PostgreSQL 18, but I think it's an interesting topic. And I'd like to give a little bit of context of not just like what the patch does, but also why we did that and what led us to making this improvement, like a bit of context of how things actually get improved in practice, right? Because it's not that you wake up one day and just say, okay, I will do fast path locking. There's reasons to do that. So I will give a bit of that. I will show you some trade-offs that we needed to do on the way, and also some challenges that still remain, right, in the code. I will also talk a little bit about how we could maybe improve and use the same idea in other places of Postgres code. And hopefully it will be useful for new contributors to actually use that. So why was I looking into this particular problem? And I will explain the problem in a minute. So it was end of 2023, customer reports poor performance, right? They have a system which was running on Xeon computers, Xeon CPUs. They upgraded to Epic machines with many more cores, and they expected to ultimately get better throughput, right? It was OLTP workload. They had a table which was partitioned with not that many partitions, maybe 20 partitions or something reasonable. And they expected to get maybe slightly worse throughput per client because the Epic has lower frequency and weaker cores, but they did expect much better throughput in the end with 100 clients or more. And that didn't happen, right? They actually saw much worse throughput with many clients for some reason. So this is a very simple example of a workload mimicking what the customer was observing. It's a PG bench with just 10 partitions, nothing insane, right? We should definitely be handling this just fine. And then there's a modification that changes the schema, which means that if you query on the new column, it can't actually eliminate partitions, right? It will still do index scan, but it can't remove some of the partitions from the plan. And the data set is very small. It's just 15 megabytes or something. And the plan that you have been seeing is something like this, right? It's append with many index scans in there, which should be super fast, ultimately, right? There's no reason why this shouldn't actually scale. But what the customers are actually seeing is something like this. And let's look at just the solid lines here, right? Those are the simple protocol. If you do the prepared statements, you will see the dashed lines, but the pattern is exactly the same. And what they saw is that after maybe 30 clients, there was no improvement in throughput, right? The performance was essentially flatlining, nothing was improving. Which is a bit sad because this machine had like 100 cores, right? So you should expect like throughput being improved up to 100 clients and then maybe flatlining. So, and the numbers there, those are numbers of partitions, right? So with 10 partitions, you get maybe 100,000 TPS. With 100 partitions, you get maybe 10,000, right? So it's like a factor of 10 slowdown with relatively modest amount of partitioning. So what could be causing this? What does every engineer do? We jump to conclusions, right? So obviously, this has to be about the number of partitions in the shared log table, because we need to log all the partitions, and this table in shared memory is split into multiple chunks, and we only have 16 of them. And if you have like many clients, they will compete for this log. So we increase that to 64. By default, that's 16. We increased that to 64 and had no impact at all, right? So this is not the problem. So at this point, it was like time for actually doing some CPU profiling and stuff like that. And we started to come up with crazy ideas, right? It could be power management, right? Like the machine could be overheating. Maybe it's like doing thermal throttling. It's not that. We have seen that in other cases, but it's not here. It was a bit weird that the behavior was much better if we disabled hyperthreading, right? So, but it's a bit sad to actually disable this on production machine, because in other cases it's actually helpful. Maybe it's actually something that is completely outside Postgres, right? We are running on operating system. We need to allocate memory. It could be, for example, malloc, and I will get to that in a minute, but it's not the main problem here. So if you do CPU profile, you will see something like this, right? And this is maybe not very, very clear, but if you do a flame chart, and by the way, the slides are already available on the conference website if you want. But if you do like a flame chart, you will see something like this. And the pink part, that's locking, right? That's obtaining the lightweight logs, which are actually not that lightweight. And like half of the time is actually spent in accessing the shared log table. And accessing a shared log table is actually quite expensive, right? Whenever you need to obtain a log on a relation, and a relation could be a table or an index or whatever, we actually need to enter something into hash tables in shared memory so that the other processes actually know about that. And this is actually quite expensive. That's exactly what all those pink lines, pink parts actually are doing. And for this reason, Postgres 9.5 came up with fast path locking. Because for a lot of actually logs, we do not care what the other backends are doing as long as they are also acquiring shared logs, right? If you look into the log modes table in Postgres documentation, you will see something like this. And there is like a huge chunk of memory, a huge chunk of the table where the logs do not actually conflict with each other, right? So if I'm obtaining a row share log, I don't care about any other backends obtaining other share log. And that was the idea behind a fast path locking, which was introduced in 9.2, which essentially adds a buffer for each backend. And you don't actually need to access the shared log table as long as you are only acquiring these shared logs, which is much cheaper because we do not need to do anything with the shared log table, right? And there is like a fairly simple protocol because you still need to care about backends that are acquiring logs that are stronger, right? If someone is obtaining an exclusive log, you still need to care about that. But it's relatively simple. It works perfectly fine. The main problem is that it only has capacity for 16 OIDs, right? So if you have, for example, 10 partitions, that's 10 OIDs. If you do have an index on each partition, that's another 10 OIDs. And you are already over the, over the capacity. And you already, when we exceed the capacity of the fastpath array, we still need to access actually the shared log table. It's like an overflow into that. And that's exactly what's biting us here, right? So that's not, like 16 OIDs is not very many. It might have been okay for very simple queries in 9.2, but even then it was possible to hit that with like a join with many tables. But now it's actually absolutely trivial to actually hit that, because once you create partitions, you will see something like that. So it's actually, I've been doing like a talk about performance archaeology, which is like an overview of performance improvements over the many years since Postgres 8.0. And one of the charts is actually for OLTP queries, where on the x-axis is the version of Postgres, and you can see the jump in between 9.1 and 9.2, right? The jump in throughput with many clients improved significantly. There are other improvements for Postgres 14 and so on, but the jump for 9.2 is pretty significant, and that's exactly the fast path locking. But we still do not benefit from that if we have too many OIDs to actually lock, right? So we want to make it larger, right? We want to make the buffer a bit larger than 16, but we also want to make it configurable, right? Because there's no way a single value would be the right number for everyone. So we want to make it dynamic, and we can't actually keep it in pgproc because that would make the fairly significant struct much larger, and we don't want that. And it wouldn't actually allow us to make an array of pgproc entries, right? So what should we do? We need to keep it somewhere else, but what data structure should we use? So this is like the first trade-off that we needed to do, because we could do a single array, like a simple array with a linear search. That wouldn't really scale to many entries, and we want to allow maybe 1,000, right? And that's a point where linear search is not very efficient. So the other option would be a hash table, like a simple hash table with open addressing and probing and all of that. That would work. It would maybe even be fast, but it wouldn't actually have a very good locality for the accesses, right? Because you would jump to one memory, one place, and maybe it's already used because there's entry with a different OID, and you would need to jump to a completely different part of the memory, and that doesn't work very well. It's fast. I mean, like, we have the random access memory, but even then, sequential accesses are much faster. So what we ended up doing is a 16-way set associative cache, which you can imagine that essentially as a hash table, but instead of individual entries, you have a buffer of 16 entries there, right? So you jump to the part of the hash table and then do linear search in that chunk. And this has like amazing properties for locality and efficiency, because if you access that, it's very likely to be in the same cache line, or you can prefetch the next cache line, and the CPUs do have that built in. And when I came up with this, I was so proud, right? Because I invented something amazing. And then I realized I've been reading papers about CPUs, about how CPUs actually do caches internally, and they use this all the time. It's like a 20 years old idea for doing caches, like level 1 cache, this, right? But still, that also means that it's like a proven thing. It's not like a silly idea. So this is what we do for fast path locking now, right? Instead of having a single chunk of 16 entries, we have an arbitrary number of those 16 entry chunks. And it's a very simple concept. It has very nice sequential access, well, within the chunk. And it doesn't have the problem with limited capacity, because you can essentially make as many groups as you want, and that's it. The one thing is that we can't resize that, right? Once you start the Postgres, this is fixed, but we can still promote to the shared log table. So it is important to make it like sufficiently large to not need the shared log table very often. So if you do that, if you increase the number of logs, if you make the array sufficiently large, and it's tied to max logs per transaction, as I will show in a minute. So if you set it to 64, which is the default, by the way, then the older, then the chart that I showed before looks a bit like this, right? So the green one, that's 18. The blue one, that's 17. And the difference between that is the improvement that you just get from this very simple optimization, right? So for the simple protocol, it's like 3 times improvement. For the prepared statements, it's like 5 times better, right? Yes, it's a very simple workload. It's a kind of constructed to actually show off the benefits. It's kind of like the best case, because your queries are probably more expensive than this, but it's still a significant improvement. So who thinks this is the end? Who thinks this is actually a happy story? Yes. Well, I'm asking this way, but obviously the answer is like, no, it's not a happy story. Because, well, this is for the 100 100 partitions where you get a very similar thing. But if you try to do that in a regular system, you will actually run into problems. And I will get to that on the next slide. But first, let's talk about the trade-offs. I already mentioned that it's tied to existing GAC configuration option, which is called max logs per transaction. We could have another GAC specifically for that, but we don't want to add more tunables, right? Because I see new configuration options more as an admission that we don't know how to do that ourselves. Therefore, we just transfer the responsibility to users, right? So And kind of like the max logs per transaction already has all the information. It's the best information about the expected number of logs that we have. So we just use that. There is no optimal value. It depends on the workload. The default value is 64, which is good for maybe a dozen partitions. If you have partitions with more entries, more partitions, you need to increase that. There's a bit of difference between how this works for the shared log table and for the fastpath logs. Because for the shared log table, we only set like a global limit, right? You just multiply that by max connections, and that says like how many logs you can have in total. It doesn't actually set like a hard limit per individual connection. For the fastpath logging, that's not the case. It's actually a hard limit on the size of the local cache, and after that, it gets promoted to the shared log table. But let's talk about actually the challenges, like the things that are not that great. Because if you do a simple benchmark with 100 partitions, and you do that with the fastpath logging on 18, what you will actually see is something like this, right? It'll be like the logging disappeared, but the that's the original chart with a lot of logging on 17. If you do this on 18, you will see this. And you will still see like roughly the same throughput, except that the time spent on logging was replaced by time spent on memory allocation, right? So we fixed one bottleneck, but it immediately ran into another one at the same throughput. So you didn't actually get anything, right? And this is just a different way to look at the CPU profile. And you can see that a lot of the time is actually spent in kernel, which is like line 10, where like 60% is spent in some sort of like a spin lock, and then page faults and all of that. And this is not really a kernel problem. Sorry, that's not a Postgres problem, and it's not even a kernel problem. It's a problem in glibc. You will not see this on like FreeBSD. You will only see this with the memory allocator in glibc. So the bottleneck is like, we are in this situation very often actually. You fix one bottleneck, and for like a very narrow case of like a query, it actually helps. But then for regular workloads, you actually run into another bottleneck, which is just very similar effect. And in this case, glibc has a problem with like allocating and deallocating memory very often, which we do here because that's what the index scans do internally. And you can fix that in this case by setting an environment variable, which kind of like adds a buffer, changes the behavior of the glibc allocator to allow, to make this more efficient. There are other bottlenecks that haven't been visible in this query, but for example, if you have a simple star join OLTP query, you will have the same problem with join planning, because we will have a very inefficient way to calculate the join order. And there are like other bottlenecks that you can also hit, and we eventually need to fix all of them to improve the throughput. And if you fix that, if you change the configuration of the environment variable to fix the allocation problem, you will see a CPU profile that looks like this. Yes, which is amazing, right? Because that's great, because we are actually spending time processing queries, not actually waiting on logs, not waiting on memory allocation. And instead of 20,000 transactions, you do like 200 of them, which is like the improvement is disproportional to how much time was actually spent on the things, because we spent half of the time on memory allocation. And now it's actually 10 times faster. So the future is like, could we use the same idea elsewhere? Right? We could maybe use a similar data structure, similar fast path approach, fast path locking elsewhere. So for example, we don't use that for buffers. We could use that for pinning and unpinning buffers. We do not consider hotness of the buffers. It's like first come, first serve basis, so maybe we could improve that. There is something we could do about NUMA, because we ignore NUMA mostly, and that's it. I'd like to shout out two people that actually helped me with this a lot. First is Robert Haas, who actually implemented the fast path locking in 9.2, and he made the code so readable that I've been able to implement this in like half a day, right? And then there was a lot of time actually spent committing that, but it was very easy to actually get it working. And Jakub Varták, who is like a support engineer in EDB, where I've been working at the time, and he was very helpful in like investigating this. I would like to thank him for that. And that's it. So any questions? I don't think we have time for questions.
I don't think we have time for questions because unfortunately.
Yes.
But thank you very much to Thomas Vondra. There's QR codes for the feedback, both here and on the door. And if you have any questions, I'm sure Thomas wants to talk to you.
Oh, yes, I will be around. So if you want to talk about this or have other ideas how to use this, let me know.